Hello everybody and welcome back. Today we're going to be solving exponential and logarithmic equations with the use of a calculator, as promised. So yeah, let's get to it. As discussed in the previous video, we talk about these one-to-one properties. We have the obvious ones that are listed there. These are great for solving any logarithmic or exponential equation. But the ones we're going to focus on today are going to be the inverse properties. So there's a cat on my desk. Hi, what's up, dude? All right, so you want to be in the video? All right, come over here. Hey, say hi. This is Bowie. What's up, Bobo? Yeah. Get out of here. He wanted some coffee. All right. So we're going to focus on these inverse properties. And yeah, I mean, that's where they're really useful, primarily for solving the exponential equations. So you can see right here, this is the one under inverses that we're really going to focus on. All right, so let's get started on these. One thing that you're going to want to have today, before we really dig in, is have your TI-84 calculator handy. If not, use that emulator that I had recommended in previous videos. I have to say, I mean, if you're watching this video, thanks for being here. In those other videos, I think the view count is something that's under 20. So you probably have not downloaded the emulator. It'd be nice if you did. It'd be helpful. Anyway, here we go. First one. We need to solve for x. And they say round to the nearest hundredth. That means we can use a calculator. So we want to know e to what power equals 5.5. That's not obvious. That's not like, oh, 2 to the x is equal to 8. Oh, x is equal to 3. Now this one is like, I don't know. Like I could estimate, I suppose. But yeah, that's a tough one. So one thing we can do is we can use the inverse property. So what's the inverse of e to the x? If you guessed ln of x, that's correct because ln is log base e, so their inverses, again, we discussed that prior. So the inverse operation for e to the x is ln. So I could take the ln of both sides. I'm going to go ln of e to the x, and I'm going to do ln of 5.5. So by taking ln of e to the x, the ln and the e essentially go away. I'm crossing them out because it just feels nice. So it leaves me with x, and that's equal to ln of 5. Now what you could do is jump on your calculator, and so this is our TI-84. You could use any other calculator. ln and log base 10 are standard buttons on pretty much any calculator. If you have a fancier calculator, sometimes you have to dig for them. But so you can see right here you have ln, and I'm going to type in 5.5. and hit enter, and I get 1.70. So this is about equal to 1.70. And then you could take that and plug it back in, and you would see that e to the 1.7 is approximately 5.5. Next. So now we have 10 to what power is equal to 16.3. I don't know, like 10 to the first is 10, 10 to the second is 100, so somewhere between 1 and 2. So what do you think we're going to do? Inverse operation. We need to free up that exponent. We have to get it down to the ground, so to speak. So I'm going to do log base 10 of both sides, or just log of both sides. So I'm going to say log of 10 to the x, and then I'm going to write a little log right here, log of 16.3. So on the left side of the equation, we're left with x, and then on the right side we have log of 16.3. Come over to my calculator, hit the log button, 16.3, and the answer is 1.21. About 1.21. So far, so good, right? I mean, I think you're probably seeing what you do. So the big takeaway is you need to isolate that exponential expression, and then so far they're already isolated, and then you do the inverse log function. So thus far we've used ln because it's the inverse of e to the x, and then we've used log because it's the inverse of 10 to the x. This next one is a little bit trickier because we have 2 to the x is equal to 23. There's a couple ways to go about doing this. You could take the ln of both sides and then use the power property, but we're not going to do that. We're going to actually really focus on using inverse operations because in algebra, that's how you solve, right? You use inverse operations to isolate x. So the inverse function for the exponential function 2 to the x power is log base 2. So I'm going to go log base 2 of both sides. So I'm really going to write this out like by itself. I want you to see the log base 2 on both sides, and then this on the left side is of 2 to the x, and on the right side it's of 23. So on the left side, the log base 2 and the base of the 2 to the x, they cancel, leaving me with x equals log base 2 of 23. And that's about equal to. So now when you go and look at a calculator, unfortunately, it's not so easy to find the a log base 2 button. There's infinitely many log functions that would exist. You can have any base so long as the base is greater than 0 and not equal to 1, right? So on the TI-84, and I'm just going to show you how to do that, you just press this math button here. I'm sure there's a faster way to do it. I'm sure there's somebody who's watching it like, oh, actually you just do second and then some function key and there's a shortcut. But this is how I know how to do it. You press math and then it's right in this menu. I'm going to push up so I can just get to the end faster. So yeah, so you would have pressed math and then option A for log base. So log base sets it up for you so you have the option to put the little base in there. So we're dealing with base 2. And then now we can plug in our argument, which is 23, and it will give us that answer. So it's 4.52. All right. So that's actually, I mean, if there's anything that we're going to do in this video, it's, I really need you to know how to use the calculator to evaluate those logarithms that aren't so common. All right. Why don't you pause the video and try this one. So if you followed my process, you would have probably run into a calculator error, right? Because you do log base 5 of both sides, and if I do log base 5 of both sides, I have log base 5 of 5 to the x equals log base 5 of negative 4.3. If you're really bringing your A game and you remember you can't take the log of a negative number, but you didn't even need to get that far, because if you look at 5 to the x, right, and you think about what you're doing, you ask yourself the question, 5 to what power is equal to what's on the other side? You can't raise a positive number to a power and have it yield a negative result. That's impossible. We know that. You can't multiply something by itself and have it magically become negative, right? So yeah. You would have done this, you would have had x equals this, and there's no result. So that was fun. So no solution. Moving on. So now these are slightly more difficult because just like with any algebraic thing, when you first started learning algebra, they just start adding more and more layers of difficulty. So this one is, just no different. What we really need to solve for first is 2 to the x. Okay, so if we can isolate 2 to the x, now we're back to the easier scenarios where you do log base 2 of both sides. But I can't do log base 2 of both sides comfortably here. Again, if you're like an expert watching this, you're going to say, actually, technically you could. You could, but that's not going to do you any kind of good. You should actually isolate the 2 to the x and it'll save you time. Otherwise, you're just stuck using log properties to like split things up and it'd be a mess. So All right, so first thing we're going to do is just add that 7 to both sides. So 7, and we have 3 times 2 to the x equals, and that's going to be 61. Then we divide both sides by 3. So now we have 2 to the x equals 61 over 3. And now we're in a position where we have to just take the log base 2 of both sides, and I'll just be sure to slide this over so we have some room to do that. And I have log base 2, log base 2, and our answer is x equals log base 2 of 61 thirds. You're more than welcome to split that into 2 logs, like log base 2 of 61 minus log base 2 of 3, and then plug it into a calculator, but why would you do that? So I'm going to go over to my calculator, go to log base. Once again, we're using log base 2, and then I'm just going to type in a fraction, and I don't know if you know about this, a shortcut for a fraction instead of writing divides, if you want to, is alpha and then F1. You can type in an actual pretty fraction where it's 61 divided by 3 and enter. So our answer is approximately 4.35. Well, yeah, 4.35. Lovely. All right then, why don't you pause the video now and try to do this one on your own. I'm going to subtract 1 from both sides, and I get 5e to the x equals 71. E to the x equals 71 fifths. Take the ln of both sides because that's my inverse function, and then I end up with x equals ln of 71 fifths. Go to our calculator. Whoops. So ln of 71 divided by 5. You could just do it this way too. I was just showing you the other fraction button for fun. 71 fifths, yep, and that's 2.65. One thing you may also be noticing is you see how I'm writing both the exact answer and the decimal side by side. If you don't have a calculator handy, you can leave your answer in terms of logs. Like you could leave your answer as ln 71 over 5 and then later solve it. I mean, that's fine. You could even plug ln 71 fifths over 5 into another equation and work with that. I mean, these are all possibilities. Example 3, this one's a little bit more difficult. Hopefully the ones that you work on will be factorable. You'll see what I mean in a second. This one is quadratic in nature. So what you do is you have to, it's just all about perception. And so you have to take this term right here, and we need to focus on rewriting e to the x so that it's by itself without that 2 there. So another way to look at e to the 2x is it's 2e squared, 2e to the x squared, okay? If you remember your properties of exponents, of course you're allowed to do that, so it's just about a little bit of manipulation there. And then now we have plus 5e to the x minus 3 equals 0. And then we want to solve for e to the x. We need to isolate that. So the way we're going to go about that is, you could just go ahead and factor right now, or we can just set up another variable temporarily. We could say something like we'll let u equal e to the x. Wherever you see an e to the x, then we're going to replace that with a u. So now we have 2u squared plus 5u minus 3 equals 0. And then that's factorable. Equals 0. 2u and u, 3 and 1, and this is plus and this is minus, right? So it's going to be 6u minus 1u is 5u positive, and the negative 3. Perfect. Oh, that was a pleasant sound. I love that. And then moving on. So we can then solve for u. So we know that 2u minus 1 equals 0, and then u plus 3 equals 0. So 2u equals 1, u equals 1/2, then u equals -3. But we were not asked to solve for u, we're asked to solve for e to the x. So this is where we take e to the x and substitute it back in. So now we have e to the x equals 1/2, and e to the x equals -3. When it's equal to -3, impossible, because again, you can't raise a positive base to a power and have it become negative, so that's gone. So we're really just left with e to the x equals 1/2. So now I could just focus on that, bring it over here, and say, all right, how do I do this again? Just take the ln of both sides, ln. So ln of e to the x leaves me with x equals ln of 1/2. Plug that into our calculator. So here we go, ln 1 divided by 2, and that's negative. Yes, logs can equal negative numbers. Negative 0.969. Yeah, sure, I'll put the 3 in there too. Okay, cool. There's that one. And so that's a bit more difficult. They don't pop up all the time, but I wanted you to see an example like that because they're very common in pre-calculus or even Algebra 2 textbooks. All right, so here's the another class of exponential function that's you've probably seen this as a logistic growth function. So if you watch some of the previous videos, we were using the calculator and the graph to figure out when, say, the left side of the equation was equal to 350. Right? So here, though, we can actually use algebra to isolate that e to the negative x and solve. So it's just a little tedious, but it's definitely doable. So the first thing I would do is just multiply both sides by this denominator. So I'm going to multiply both sides of the equation by 1 plus e to the negative x. So I'm going to take that, and I'm going to put 1 over here. I'm going to multiply the other side by this one here. So what occurs is these go away, and then we have 400 equals 350 times 1 plus e to the negative x. So then I'm going to distribute that. I get 350 plus 350 e to the negative x, and then we just keep isolating. So then I'm going to subtract the 350 from both sides. So then I have minus 350. So I have 50 equals 350 e to the negative x. Divide both sides by 350, so e to the negative x is equal to 50 over 350. E to the negative x, may as well reduce that fraction, equals 1/7. And then we're right back to where we'd normally be. Take the ln of both sides, ln, and I have this time got to be careful. You have negative x equals ln 1/7. Negative x equals, then you multiply both sides by -1, and you get x equals negative ln 1/7, which is about equal to negative ln 1 divided by 7. Be sure to close that parenthesis, just in case. I didn't do it on the last one, but I think it's fine. It's going to be, yeah, that's right, 1.95. All right, so there's that one. And lastly, I know that you're stuck around for a long time, and it is what it is. So log equation using properties. So a lot of times students get a little bit intimidated by a problem that looks like this. In order to solve a log equation, it'd be really great to use that one-to-one property. In this particular instance, if you have ln on one side, you need to have one ln, like scenario, on the other. That way you can set their arguments equal to each other. If there's any coefficients out in front, you got to bring them up as powers, and then you can set the arguments equal to each other. That's just the way it is. So in this case, how can we get a single logarithm on the right side? We have to use that quotient property. So I'm going to rewrite this as ln x plus 5 equals ln. And you know what? Just for fun, let's color code our arguments red. So, and then we have ln of x minus 1 over x plus 1. Okay, and then now you can set the arguments equal to each other. Sorry for the sounds in the background. It's just the way things have to be. X plus 5 equals x minus 1 over x plus 1. And, all right, sorry, there's an interruption there. So then I'm going to multiply both sides by x plus 1. And we have x plus 1 times x plus 5 equals x minus 1. X squared plus 6x plus 5 equals x minus 1 minus x plus 1 plus 1. And then we have x squared plus 5x plus 6 equals 0. Let's just slide this over here a little bit. I love when that happens. Hold on. Slide this right here. And then we have, then this factors nicely. X 2, 3 plus plus. Awesome. So x equals negative 2 and negative 3. That's lovely, but let's go back and check. This was a log equation, so do they both check out? Now, a lot of people are like, oh no, x is negative, I can't use it. Actually, look in the original and make sure you don't get negative results. On the left side, for example, when I plug in negative 2 or negative 3, negative 2 or negative 3 plus 5, they're both positive numbers. On the right side, we have a little bit more of a problem, I think. If I plug in negative 2, let's just compartmentalize here. If I plug in negative 2, I'm going to get ln of negative 2 minus 1 over negative 2 plus 1, which becomes ln of negative 3 over negative 1, so it's positive 3. So it checks out. And then we'll do the same with negative 3. So that's going to be ln of negative 4 over ln negative 2 becomes ln 2. It checks out. So yeah, we're good. So our final answer is x is equal to either negative 2 or negative 3. Hopefully that was helpful, and be safe. Take care.